Benjamin, you just missed. We were talking about hiking, where I'm planning to go hiking next weekend in Sydney, and it turns out
hiking is fun.
Yeah, it's right next to the research facility where Helen used to work. Like, are you physically based there?
Oh yeah, no, I am. Yeah, that's where my Wombat is. That's where I go, and I just don't have to be there as often as I used to. So yeah, well,
Okay.
I plan my time a bit. So sorry, Benjamin, I don't know whereabouts you're based.
Not too far from where you are.
Okay.
I'm in California.
All right, I was just across the pond.
Kovi and I have taken to joking recently that it's difficult to schedule our recordings with a planet in the way. So
yeah. This is my second meeting with a planet in the way, so I've already had one this morning. So
oh wow, Earth is a pain.
Yeah, it would be better if it was flat, right?
Oh god, it's so much easier. Then everyone's like, "Can you see me waving?" joke would work because we could.
I feel like nobody knows that better than the scientists who have these big international collaborations that require meetings at ungodly hours. It's like, the scientists want it to be flat. Just believe us when we tell you that it's not.
Yeah, I did a very silly thing, and it sounded great at the time that I agreed to organise an international school in Italy with someone who was based in Vienna, someone who was based in Utah, and me in Sydney. And we were like, oh, this is amazing. Look at us being a really international crew. And then we tried to organise our first meeting, and it was like, oh.
Mm-hmm.
And it sort of took in turns for somebody to be up at 3 o'clock in the morning, basically, because there's no way getting around that.
Well, I'm very glad that we all caught each other now in this slot. Hopefully, we're all awake, and you're right. Honestly, I'm thrilled, and I can't believe it took this long to get you on the show. But I am very, very honored and grateful to introduce Helen Maynard Casley as our guest for this week's episode of Science Actually Presents the Nerd and the Scientist. Helen is the principal instrument scientist at ANSTO, which is the Australian Nuclear Science and Technology Organization. I hope I got that right.
Yep. Yeah. I should say I'm a principal scientist, not the principal scientist. I would love to be.
Is there a the principal scientist? Or are there
not anymore. Used to that role should be chief scientist, and unfortunately, we don't have one at the moment. But one day, that's the goal. That's the goal.
I guess my assumption is principal scientist is not like principal of a high school or something like that. There are many principals, I guess, depending on which instrument they're working on.
Yeah, exactly. Yeah.
And you work on one of the coolest named instruments, the Wombat, which you just mentioned before in the intro. Firstly, welcome. Secondly, do you want to tell us a little bit about what it is you do with this magical Wombat machine?
This magical Wombat, yeah. So hello everybody. It's great to be here. So what is Wombat? So I work at the only nuclear reactor in Australia. The nuclear reactor is mainly there to make medical isotopes. So for imaging and things like this. But they allowed some of us scientists to sort of use the byproduct that comes off with any nuclear reactor, and that is a lot of neutrons. And so our institute's called the Australian Centre for Neutron Scattering, and we have 15 different instruments that sort of come off the reactor. So essentially, neutron scattering started, it's actually a byproduct of the Manhattan Project. The first scientist who got involved with it was Ernest Woolen, who was actually in the room where it happened with Ernest Fermi and underneath the baseball courts in the University of Chicago, where the first mini reactor happened, and was involved in the X-11 reactor at Oak Ridge. So once they had made enough plutonium and uranium for what they needed to do, they were looking about what else they could use it for. And Ernest Woolen and a guy called Clifford Scholl came to this idea that they could use it to do some scattering experiments. So by then, X-ray scattering was pretty established, and they were a bit like, the physics should work pretty well. Plus, neutrons are sensitive to magnetic. So they've got a little magnetic moment. So we should be able to see like magnetic structure. So that was kind of exciting. And so legend has it that Ernest Woolen stole a X-ray diffraction device from the University of Chicago in the middle of the night and drove it down to Tennessee. And there is this letter, this is a beautiful letter with him writing to the head of Oak Ridge, or Clinton Research Laboratories as it was at the time, and going, excuse me, can I drill a hole in your reactor? I would like to try something. And he did, drilled a hole. He was allowed to do it, drilled a hole, got a little beam. So by drilling a hole, he got a little beam of neutrons coming out. He put a piece of magnetite at the end of that beam, and he got some scattering that could only have come from the way that the magnetic moments are aligned in the sample. So that sort of begun the whole field. There are numerous neutron sources all around the world. I first encountered one in the UK as a very impressionable 21-year-old, and I was a bit like, these are big facilities, lots of different instruments. They're like, there's gangplanks, there's compressors, there's things going whoosh. It's basically a James Bond baddie layer. That's essentially what it looks like. And I was pretty captivated. And I've sort of followed these around the world. And there was also, I has to be say, a point during my PhD where I was in the one in France doing an experiment. And I was with my very harassed PhD supervisor, obviously teaching research funds and things like this. We broke the instrument a little bit. So when you break the instrument on these experiments, you have to ring up the instrument scientist and go, hi, can you help? And the guy said to me, and I quote, give me half an hour to ski down the mountain and I'll be with you. And I was like, I want this person's job.
Yeah.
So that's the job I have right now. I mean, I don't have any mountains to ski down, but I do have beaches to sit on. So Wombat is one of these instruments. We take neutrons out of our reactor. We put materials in the way. We get scattering patterns off. The instruments, we've got 15 of them. The cute thing about our institute is we name them all after animals, Australian fauna. There is actually one that's named after a Taiwanese deer, and there's also a German bird for reasons, but they're all named after Australian animals, and that vaguely describes a little bit about what they do. We're interested in basically our instrument tells you where your atoms are, and because Wombat is the high intensity diffractometer, so it's fat peaks but very fast, because wombats are quite intense animals. We're all about changing the conditions of our samples, putting them under extreme conditions and seeing how your atoms, how your structures are actually responding. And yeah, so the day-to-day of how it works is that every 6 months, any scientist in the world can write to us and go, hey, I would like to try this experiment on Wombat. And it goes to an assessment panel who decide on the, independent of us, of the best science to do. And we then it sort of comes to us and we help them run it. So that's 2/3 of my job is maintaining the Wombat, keeping it going, and helping other scientists use it. So every week is bonkers. Like every week you sometimes have an engineer coming to do something, we have biologists, we have chemists, you know, who want to do crazy things to their samples, and then the other third is I get to do my own research. So yeah, it's that's pretty much me in a nutshell in terms of a job. And people pay me for this, it's crazy.
Spoken like a true scientist. I love that. The glee. Yeah.
So because you don't have a mountain to ski, you have a beach to sit on until
Yeah,
such time someone needs you to help them blast
yeah,
particles at things.
yeah. Pretty much, that's it. Yeah.
Oh
So
God.
yeah, that's sort of it. Often it is because the Wombat is actually an incredibly reliable instrument. Actually, she's done really well. The people who built it originally have done an amazing job. So usually it's just silly things like the instrument's not working, and what it was is that the phone was right next to our motion stop button, and people would be on the phone and they would lean on the motion stop button, and then they would ring me and go, "I can't collect data," and I'm like, "Is the motion stop green or red?" And they're like, "Oh, it's red." I'm like, "Did you lean on it?" Like, yes. So a lot of the time it is sort of human things or like silly little things like the computer, the software, the control software gets itself. So not too much dramatic happens, which is good.
Benjamin, I saw your face during the explanation of neutron scattering and like drilling into a reactor just kind of drop.
I just love
People
that
who are
kind of
just listening.
stuff. I've seen pictures of the very first nuclear reactor in this big, massive cement block.
And they used to like manually put in the control rods.
Yeah.
I love these pictures of they're all in white coats, and that's how they would literally there would be people like it's a big concrete wall with loads of holes in it, and they would literally be there pulling and pushing them in like by hand, which is just like what happens if you just whoops.
Oh God.
Look up the pictures, like Javi. They're beautiful. These black and white photos. This massive, massive thing. And people just milling about outside with like no real understanding of what's inside.
This is all happening under the bleachers at the University of Chicago, right?
No, this is
underground.
The first one. No, so the X11's not underground. Actually, it's
Oh.
in Oak Ridge, and it's just a big wall of concrete. I've been privileged enough to visit it because because Oak Ridge obviously has lots of reactors, but it also has a neutron source, 2 neutron sources where I've got a lot of colleagues. And in fact, the only instrument in the world that is sort of identical to Wombat is there. So we sort of do a little bit of, I ring up Mateus, who runs it sometimes. I'm like, "Hey, how's it going?" His instrument's called 1 squared. And we're just like, "So this happened." I'm like, "Oh yeah, that happened to us too." And so, yeah, it's a nice little network. But he was like, "Do you want to see X11?" Like, yeah.
I had to look up the photo like while we were talking because, you were not wrong. Like they're just pushing. They've just got like a long stick and they're just like shoving the rods into these.
Yeah, it's insane. It's now like a heritage listed thing. It's decommissioned now, but it's a shame it's on a very secure site. But it's a part of US and scientific history for people to visit and to think about what it achieved as well. I think we have to pause a little bit and the implications that had.
Yeah. Well, that was something that came across my mind was like thinking about the use cases for this sort of technology and how great it is to see that in Australia it seems like OPAL, right, which is the open pool Australian light water reactor, right? How it's being used for, as you said, like mostly medical purposes, and then in your free time, you're using it to...
Well, yeah, medical and research. Yeah. It was purpose-built as a research reactor, so, yeah.
Yeah. That's cool. It's nice to see that there's like, I don't know, I feel like in some contexts, like nuclear just becomes a dirty word, and I feel like it would be a shame if all of this, like, potentially, world-changing, technology-changing technology, for lack of a better phrase, was not used just because there are these other associations.
No, I mean, obviously, I've been worked in the field for a while, and there's a lot of there's a lot of connotations for nuclear and things like this, and I think it's good as a country we sort of pause and think about it and things like that. But the research reactors are pretty amazing in what they've achieved. I mean, it's the reason that one of the big discoveries from neutron reactors was giant magneto resistance, which is why you're able to have a mobile phone that sits in your pocket, because that's how we mainly store information at the moment until quantum computing catches up. So without that sort of discovery of magnetic storage, which could have only come from neutron scattering, that's a massive technological leap. And yeah, the Opal reactor was the first of its kind in the world to run off low enriched uranium, because Australia is signatories to the non-proliferation of nuclear weapons. So we're not allowed to have any enriched uranium in the country. It was sort of like, this can't happen, it can't work. It was actually an Argentinian company, engineering company, that built it, called INVAP. And they've done an amazing job. It's brilliant. And now they're building one in Buenos Aires, so that they'll have a research reactor and medical isotopes making as well. So yeah, so I think it was cool that we were sort of the test bed in some ways, and hopefully more of these little reactors will sort of pop up for science and medical isotopes around the world.
How big is this little reactor?
The actual reactor itself is the size of a washing machine.
That's it?
Yeah, that's it. And she does pretty good. But obviously the construction around it is very, very different. So so it's a lot of concrete, a lot of shielding and things like this. And then you've got us, the ACNS, the Australian Centre for Neutron Scattering, tagged on the side, because our instrument, we've got a few that are actually at the reactor face that have to be there because they need sort of as hot a neutron as they possibly can have. We've then got a whole suite of instruments like us. We're thermal neutrons, so we're room temperature neutrons. So essentially, the pipe, it's a bit more sophisticated than a lead pipe these days, but essentially that's how it started. And we let the neutrons bounce down. We now sort of guide them, but neutron guides are quite interesting physics, like how do you reflect a neutron? We mainly take room temperature ones because their wavelength is about the same as the distance between atoms. But we've got a cold source, so they actually also run the neutrons through super chilled helium. That slows the neutrons down, makes their wavelength longer, and then they're good at seeing bigger things, so cells and things like this. Those instruments, so they're called the small angle instruments. There's two of them, which are called Bilby and Quokka, and they are massive because you have to go really long way to see a small angle, right? So, and they're massive vacuum tanks. They look like old school trains, steam trains. That's exactly what you can sort of picture, the sort of size of them, and so they sort of extend out. The really funny story about Bilby is it was meant to be called Goanna, because they're long things. So goanna is a lace monitor in Australia. They're these long animals, and with long tails, and they're curious. They're funny little animals. But then they employed a woman called Anna to build goanna, and she was like, "I'm not going to be Anna who built goanna. Like that's not going to happen." So they changed the name for her. So that's kind of cute.
Amazing.
I'm looking up a goanna.
Oh yeah, you do. We have them on site. I had to call security on one the other day. He was not impressed with me because we have a big fence around site. If we see one or a kangaroo on site, we have to call somebody on them to come and take them off, because you don't want them getting trapped and stuff. So
naturally, you wouldn't want to goanna inside your nuclear reactor and then bad things.
No, that's how Godzilla happens. So.
Oh, I was going to go for Godzilla, but yes, that's exactly how Godzilla happened.
Although if it was a quokka, I wouldn't mind a 7-foot tall quokka. That would
giant
be
quokka. What's it going to do? Smile at you?
But aggressively.
Good times.
In terms of animals. Sorry, I know, Benjamin, you probably have a lot of questions about.
No, go. This is great.
I just you mentioned animals, and there was something I noticed while doing research for the show that I don't know if I had known this before. I'm sure you probably mentioned it to me over beers once, and I might have forgotten. The Christmas lecturer thing, which is brilliant. So I had no recollection of that being a thing. So for context, the Christmas lecturer is something that has been happening for like 200 years in London. I think Faraday was the one who started it. It's this lecture series where scientists do like these massive public outreach events, and they do these cool experiments for kids, and it's like a massive production every year. And people like Carl Sagan and David Attenborough
I've
have
seen the
been
Sagan ones.
lecturers.
Yeah, they're great.
Yeah. I'm clearly uneducated. I need to go back and watch them. But I didn't realize that you were like one of the researchers involved in the Christmas lecturers. And the animal connection is the fact that, of all things, you were working on leaf cutter ants.
Yeah.
How?
Yeah.
What?
Yeah. So that was the best Christmas temp job ever, basically. So yeah, to give you context, if you grow up in the UK and you want to be a scientist, especially like my era, you would watch these lectures. So they are broadcasted like between Christmas and New Year. So that sort of like, time when nothing else happened. There was always the Royal Institution Christmas lectures on TV, and they got some amazing people. And one person who really influenced me was Monica Grady when she did hers on planetary sciences. So funny where I ended up. And later on as an undergraduate, she lectured. I got a guest lecture from her, and I was like so fangirling. It was amazing. So I was finishing my PhD. Actually, I'd done a short postdoc, and I kind of wanted to dabble a bit with science communication. And in the UK at that point, there were a few sort of masters and things you could do, but the other way of sort of like getting science communication training is to do a job with the Royal Institution. So they are this essentially public building in the middle of Mayfair that's very, very posh, and it's the home of some, I think something like 80, maybe only 6, but a lot of elements were literally discovered in that building. For me as a crystallographer, so that's the field that I work in, that's where 2 of the Nobel Prize winners, Lawrence and Henry Bragg, worked. They were their father and son, but they were both directors of the Royal Institution at different times. And so all of their, like literally their Nobel Prizes are in the archives there. So I got to like hold them and see them, and all their notes as well and things like this. So that was incredible. So so every year, I think they still do it. So they pick a prominent scientist to give the lectures, as you say, Carl Sagan and David Attenborough have been some of the people, but yeah, Monica Grady was still my favourite. And then they picked a guy called Mark Miodownik, who's a materials researcher and all-round amazing dude. And they were looking for a researcher to assist that person. And I managed to get that job. And nice. I never forget the interview with Mark. And he was just like, so Helen, if I asked you to make me a flea circus, how would you go about doing that? And I was a bit like, I think my first reaction was I would panic. And then I sort of forgotten about this. And then day one, we went out for lunch, I and the director of public programs at the time. And he just turned around to me, so about that flea circus. And I was like, oh, so you really weren't joking. And so essentially I sort of scrambled around and had to find random things. So it was all, his lectures were all about scale and size and essentially how different things work on different scales. And he was very influenced by, I think it was a lecturer, something that JBS Haldane, so this one of these gentleman scientists who was a biologist, this idea that, and because I think the Burj Khalifa, this biggest building in the world, was being built, this idea that if you were as a mouse, if you the mouse jumped off the Burj Khalifa, it would be okay. It would land on the ground fine and scuttle away. If you're a dog, you would break a few bones. If you're a person, you're splatted. And so this concept of how these different scales in biology, materials, and things like this all influences us. So, of course, flea circuses are like the ultimate of that. So fleas being very, very strong compared to their tiny, tiny size. And I was a bit like, okay. So it turns out the answer to finding flea circuses and leaf cutter ants demonstrations are PhD students and PhD students in entomology. So I found a guy who was doing his PhD in Cambridge, and as a side was really interested in sort of Victorian circus drama. And so he had like lots of like, you know, sort of vaudeville type things and things like this, and with cosplay and everything. And he was really interested in getting a flea circus. He even had like, so when I say like, so at some point flea circuses were like fake, like they used to be sometimes done with magnets, but back in the Victorian eras they were actual flea circuses. So actually that, and
Really?
people would have like little tiny little carriages that the fleas could move, and they would give them like little swords because they would just wave their legs around and it would look like they're fighting and things like this. And there's all this, and this is sort of like part of sort of history and stuff. So that's what Mark wanted. He wanted actual fleas. Now my problem stroke good thing is that human fleas, which you actually, so fleas are different species compared to the people that the creatures they live on. So human fleas are larger than cat and dog fleas. They're different species. And cat and dog fleas are tiny. They're really, they're much smaller, and they're actually, this doesn't work. You can't do a flea circus with a cat and a dog flea, for instance. So I couldn't go and find a friend's pet and like, you know, dust some off, get some fleas. So my problem was getting fleas, because luckily human fleas are almost eradicated in the UK, barring some special circumstances. And so I spoke to the student, and he was like, yeah, I've got all the stuff for the circus, but I don't have any fleas. So, you know, if you could get me some fleas, then we're all sorted. And he sort of said, and I was like, okay, but apparently badger and hedgehog fleas are the sort of sizes you want. And
Noted.
so there is a hedgehog hospital in the UK called St Tiddlywinkles. I remember from my childhood. Yeah, I know. It's like the whole of the UK is just so cute. And so I rang them up and I was like, hi, can I have some of your fleas? And they were like,
it's for science.
Sure. I know. We got tons of them. So I remember.
That's kind of in the same vein of like, hi, can I drill a hole in your reactor?
Yeah, I know. Yeah, it's the sort of, you know, I'm very happy.
Just love helping.
Yeah, exactly. So yeah, so that was part of it. And then Mark also wanted a demonstration of leafcutter ants, so found another PhD student who was investigating them, and I had to make them their own little like run around to keep them going. Oh gosh, the risk assessments I had to do, because the RI is a historic building. Had to keep them up in the loft for a while because that was the only place that was warm enough for them. But also there are scientific instruments there, and so they were like terrified that they would get loose and they would start like, you know, eating through things and stuff like that. So it was so I had to make like a little moat around them, and then there was like secondary containment and things like this. So yeah, it was a fun job. There was a lot of the other thing I'd had to do was work out the exact amount of jelly balloon. We had to go find the Metropolitan Police, who gave us a load of ballistics gelatine, so that we could I think the big first demo was this demonstrating JBS Haldane's theory, that if you were a little hamster and if you were a dog, you would react very differently if you were dropped from a height. And we played with the audience. We had like an actual hamster and an actual dog, and there was like a box, and like, you know, you look like you're going to crane it up, and at the last minute it was like, we're not actually going to do this. We brought out what we called the crash test pets, and we made these giant pink jelly balloons, and they had like, you know, the yellow and black symbols on them. So yeah, it was it was a lot of science, but a lot of show personship as well. So it was a bit of a bonkers job to do, and then I moved to Australia.
What's the next most bonkers thing I can do after this? Yeah, Australia will do it.
A mouse could survive a fall from the top of Burj Khalifa?
I think that's the idea. I'm not entirely sure
you would get stuck on that.
It yet.
I'm stuck on that. I'm sorry. I mean, I really want to test it, like really, and I maybe shouldn't have admitted that, but it just doesn't make sense.
I think there's the concept that the terminal velocity under gravity wouldn't be enough, that the force that they hit wouldn't be enough, that they're probably okay. Whereas, as I say, we would literally be paced.
Oh yeah, I know we'd be paced, but Burj Khalifa gives you time.
Think about how pasty you will be.
I'm very glad we went on that tangent. That was wild.
Well, good to know about the mice. I have a note when I'm at the top of the Burj Khalifa that I need to get to someone at the bottom. I'll just tie it to the mouse and toss it off.
No, they check you when you go up in the elevator at the Burj Khalifa. They check you. They pat you down for mice. So
we got another mice guy.
Yeah. Like at the airport where they have that bin of bottles of water. They just have like a little bin of mice.
Bin of mice that people just wanted to throw off a building.
I don't know how to segue from that back to the rest of science. But I know, Benjamin, you had a lot of questions that you did want to ask about planetary science.
Well, I mean, I in prepping for the show, I watched a lot of talks you gave about ice worlds and stuff like that, and from talking about tossing mice off of buildings, which is still very, 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 very fun. Well, ice worlds, Pluto, planet or not?
It's King of the Dwarfs.
I like that answer.
Yeah, I mean, as a geologist, geophysicist, I should be like, look, it's round, it's spherical. It should be a planet. But that choice was taken away from us by astronomers.
Don't look at me. I didn't vote on that.
Anyway, I'm generally like, astronomers are my mortal enemies often, and with the exception of a few people, I essentially, they were the ones who got to make that definition. So I tend to sort of say, look, yes, it was rubbish that it's not called a planet anymore, but there's a whole new heap of other planets now. So that's cool. And it's the biggest one. Well, maybe not the biggest, but let's go with it's the best known one.
There's one. What's bigger than Pluto? That's in that.
I think Eris. I think that was the problem. That Eris is actually slightly bigger than Pluto.
Is it?
I think that was sort of one of the nails in the coffin for poor Pluto.
Poor Pluto. It's too Earth-centric, these definitions of what qualifies as a... The rules are, it has to be round, it has to orbit the sun, it has to clear its orbit of debris. But some planets that we have not done all those things yet.
Yep.
And those are still planets.
Yeah.
And maybe not in the lifetime of some scientists here, but has Pluto had the time to clear its orbit yet? But it's gonna.
Well, I don't know. I think Sharon might have something to say about that. Because I don't know. It's. I find it very interesting, but I just was a bit like, as a geologist or a geophysicist, it's a sort of basic, like, the fact that it's sorry, I'm going to swear now, but it's got its shit together enough to be spherical is enough for me. So that I feel like should be the definition. But I think a lot of geologists feel that way. But we weren't asked about what it makes a planet. It was the astronomers who got to decide it. So it's like, fine. I mean, there are obviously graduations of being spherical. So yeah, that's also a thing.
Yeah. What is that word? Spheriness.
Yeah, I like spheriness. I like that.
Spheriness.
Very body.
Spheritude. You can measure how many spheritons it has to make it spherical. Yeah.
But I mean, Pluto is flat like all the other planets, isn't it?
No, don't go there.
Sorry.
Yeah, but we have turtles all the way down. Pluto has hamsters all the way down. That's probably what it was.
The hamsters that, at least I'm here and not jumping off the Burj Khalifa.
I'm curious. I know that you mentioned very briefly when we were discussing like your time allocation at ANSTO, and I'm curious if you can explain to folks how neutron scattering kind of relates and connects to your your work on planetary science.
Yeah, because I think probably anyone listening at this point is like, she said she's a neutron. What? Where's this planetary come in? So, so that was like, as I said, I was very influenced by Monica Grady and some of the original Planet programs that were on in the UK, sort of pre Professor Cox, I should say. I don't need a particle physicist to tell me how to do planets. Sorry, that's also another gripe. Yeah, so when I got to doing undergrad and stuff, I really sort of wanted to follow my heart at doing stuff. And there was this one course undergraduate that was called Planetary Sciences. And I was a bit like, and I remember my parents just really panicking and like, what kind of job are you going to get with that as a degree? And I was like, I have no idea, but it will be fun. And so I did that, and it was all sort of planetary science. It was even one of the things I love about planetary science is how dynamic it is. So when I started, they weren't teaching us, so it was between geology and physics, I should say. So geology and astronomy was essentially what the course was. So we went having to go and do lots of observational astronomy and then lots of igneous petrology lectures, like sitting there looking under a microscope. So it was microscopes and telescopes. It was a lot of fun. I feel like we just did the best bits of everything. But yeah, they didn't teach us sedimentology at that point, which all the other geologists were doing because there was no water really found on anything. But during my undergraduate was when Opportunity and Spirit landed on Mars, and the first thing they saw was evidence of sedimentology. So by the time I was in my third year, the first years were being taught sedimentology. So this is like how dynamic it is as a subject and things like this. And basically, I got to my fourth year and I learned a bit about sort of diffraction and crystallography, which is what I apply these days. And what it occurred to me is that the way that people become planetary scientists, and because they're sort of quite hard to get, like there aren't really planetary science departments and things like this, is often they're chemists, they're geologists, they're physicists, they're plying their trade to understanding stuff about planets. So I think one of my colleagues once said, planetary science is the ultimate applied science. And I was like, okay, I like that as an idea. So it occurred to me that I needed to get a trade. That if I was going to be working planetary sciences, I needed to go and find a trade. And by now I had discovered neutron scattering and, the James Bond baddie thing. And I was just like, this looks great. I could go live in an evil layer and do this. So essentially, then I managed to get a PhD position up in Edinburgh to learn high pressure neutron diffraction because I was a bit like, I want to know what's in the inside of planets. And in that case, so neutrons are much better than X-rays to some extent. So anything we know in terms of the structure of matter has come from X-rays and neutron, smaller amount of neutron. It's a bit specials, but essentially it's how we know where all atoms are. And then from then on, you can get on with physical properties, so how strong things are. So how we can sort of know about the materials on the interior of our planet and all other planets as well. And I got really sort of obsessed with this idea of knowing more about the interiors of icy moons and the icy gas giants, where the materials aren't rocks so much. They're not so much like silicate metals that we have on Earth. When we get further out in the outer solar system, all these materials are water dominated, and they have a lot of light elements. So the good example to start with perhaps is Uranus and Neptune, our icy gas giants, which are mainly made out of methane, water, and ammonia. So very, very simple fundamental molecules. And X-rays are quite good at these, but essentially the way that an X-ray interacts with an element is dependent on how many electrons it has in its outer shell. And so the scattering goes up as you go down the periodic table. So hydrogen, nitrogen, carbon, and oxygen tend to not scatter very well at all. Neutrons scatter, instead of off the electron cloud, they actually scatter off the nucleus, which is why they're sensitive to magnetism, but it means that it's more to do with the strong nuclear force of the nuclei. The practical upshot is that the scattering is really, really random across the periodic table, really, really random. And there's some really interesting little material tricks, like vanadium, the metal vanadium, is because of its coherent and incoherent component, because there's two different components to the scatter, it's invisible to neutrons. Essentially, there's sort of like the Brits have a phrase of like, well, that's about as useful as a chocolate teapot. You could say the same, that, you know, vanadium is about as useful to neutron scattering. So it's essentially the idea. If you want to study vanadium, you do not use neutron scattering. However, if you want to put your sample into the beam and you want to hold it in something, you could put it in vanadium. It's great. So we have a lot of vanadium cans for that reason. So there's all these engineering tricks, which it means that you can construct very weird sample environments around your sample. You can do things to your sample. You can put them under pressure. You can put them under temperature. And it doesn't matter that they're made out of light elements. You can get a lot of information about them. So my PhD was mainly on methane, high pressure methane structures. So I know far, far too much about methane. And so that was a lot of fun. Did a lot of neutron scattering, lots of things going boom and things like this. So that's sort of like where the sort of background happened, and sort of applying this trade of applying neutron scattering to studying these planetary materials, because they're not, it's hard to look at them elsewhere. And then more and more sort of moved away from high pressure to just low temperature, which I say just. And it would seem that now we sort of actually even have our own field. So that in the last few years, I've had a long time of like people asking me, so what is your science? And I'm like, well, I'm a bit of this, I'm a bit of that. And it depends who I'm talking to. Whereas now I feel like I have a label that I'm happy with. And that is a cryomineralogist. So I'm interested in minerals, but these are minerals that will melt at our temperatures. So these are the things that are all over icy moons and things like Titan and Pluto and Europa and things like this. So essentially, because again neutrons can barrel through things, we've got big cryostats. We put our samples, often they're gases or liquids, we're condensing them in and studying like what their basic crystal structures are. Once we know their crystal structures, we can go forwards with finding more about their physical properties. And the ultimate aim is to describe and to understand all the landforms that we're seeing from all of the probes out there. So that's sort of essentially how sort of my research works, and I collaborate with people sort of across the globe to do this, which is fun.
So you just try to recreate the surface of these worlds here. That must, what kind of containment unit do you use, or system do you use to make that kind of pressure? How big or massive or thick must that thing be? And then you have to keep it that way.
Yeah. So at the moment, so the pressures, the press itself that would use to sort of get to do the sort of interior stuff, there's a few different ways of doing it, but essentially it's an opposed anvil device. So we use two sort of sintered diamond anvils, and we make a sample very, very small and we compress it. We use, good old Newtonian force over unit. You put a reasonable amount of force over a small area and you get a large pressure. So, and this big things are big press and things like this. We tend to only really do, it's quite hard to do temperature and pressure at the same time. And generally you don't need to, because as soon as you dig into the center of these planets, so the surface temperature of, for instance, of Titan is minus 180 degrees C. As soon as you start digging in, the geothermal energy that's there means that the warmth is going up. And so by the time you're getting, that's why they have the ocean worlds, they have the oceans underneath there. And so by the time you get into the rocks below, you're actually at room temperature. But the surface minerals, which is more what I've been doing, we've got these big, because neutron sources were sort of designed around magnetism, and generally magnetism is something you want to understand very cold. A colleague put this to me. So what happens is that when you cool things down, because at room temperature, things are actually on an atomic level vibrating a lot. The vibrations, room temperature is actually quite warm. And so that blurs out the magnetism. So if you really want to understand what he calls the soul of your material, a very poetic colleague of mine, that you really want to get it really, really cold so that you don't have that thermal vibration. So as a field, we have lots of different ways of getting things to incredibly low temperatures. 4 Kelvin, so minus 269 degrees C is every day. It's an everyday thing for us. Going a little bit below 4 Kelvin is a little bit more challenging. So down to millikelvin is more challenging, but literally 4 Kelvin is an everyday thing at a neutron facility. So going to planetary surface temperatures. So it's a warm day on Titan is minus 180. We're looking at around minus 140, 120 for Europa. Pluto actually was one that other people have struggled with because it's like it varies between 40 Kelvin to 60 Kelvin. But again, that's easy. I can do that. So they're big cryostats and they're run of the mill. And so all I've had to do is adapt to find ways to condense my samples in there. And that's the thing that we've been doing.
Wow.
Ridiculous.
Yeah. The fun thing is it's exposed a lot of fundamental things that we didn't know. So for instance, Titan, it has a large atmosphere. It's the reason everyone's excited about it because its atmosphere is nitrogen and methane. No one quite understands why the methane's there, but it's there, which is kind of interesting. And over the sort of 4 billion years that atmosphere has been sat there, it's been radicalized by the solar wind and the radiation from Saturn itself. And so when the nitrogen and the methane sort of become radicalized, they start forming bigger molecules, hydrocarbons and nitriles. They're a bit heavy to hold up, so they rain down on the surface. And because this has happened for 4 billion years or so, they think there's like a 2 to 3, this is off of results from Cassini, 2 to 3 kilometer thick layer of these hydrocarbons and nitriles. So all of the interesting features that we're seeing on Titan, everyone assumed would be water ice because it is on the other icy moons, but it's not on Titan. It's all these small organic molecules. And there's an observation of about 18 of them in the atmosphere. So these are like our sort of basic building blocks. And about a few years ago, I sort of just went, okay, we'll know all the crystal structures of those. These are all, fundamental gases and things like this, things like alene and propine and things like this, like three carbons and 2 hydrogens. I'm like, yeah, this would be done. But no, it hasn't. And so what it discovered was there's all these sort of very fundamental small molecules that we have no idea how they crystallize. And that's sort of what I've been working through with a very talented bunch of students. And it's been a lot of fun. And, I go to chemical crystallography conferences and they're like, I can't believe you're finding new results on something that is so small and fundamental. And I'm just like, but I'm doing it because I want to know their physical properties. So there's sort of like no one else would have probably thought about that. And then the next complication was we found that when we mix them, they sometimes form new materials. So
wow,
yeah,
it just wants to become something else.
I know, exactly. So benzene and ethane. So benzene's the ring molecules, 200 years this week, I think, since it was discovered, which is a really cool little molecule and things like this. And it's a molecule that has a lot of cool history for crystallographers as well. It was the first molecular structure. So for a long, long, long time, people thought that the benzene ring, there was no way it could be flat. They were like, oh no, it definitely has to be kinked and stuff like this. And then an amazing woman called Kathleen Lonsdale, one of my scientific heroes, was the first person to say, no, actually, it's flat. Anyway, so benzene and then ethane, the small molecule that, there's lakes on Titan that we know methane and ethane mixtures. And this work came from the Planetary Ices group at JPL. And they were looking at the shores of Titan. And they were seeing that there was some slightly different radar characteristics there. So they're like, oh. And then there were like also dried up lake beds as well. And so they were like, what could be, and on Earth we would call these the potential of evaporite minerals. So if you take a plane across Australia, you see those same dried up lakes, and these are minerals that have come because the water has evaporated and left the bath scum behind, essentially. And they were like, so we can understand what that is in an Earth context with water, but what is that in a Titan context? So they started sort of flushing a lot of these small molecules that with ethane, with liquid ethane. And they did it with benzene. They had like a little crystal of benzene, and then they flushed it with ethane. I think it was literally the first experiment they did. And the crystal changed completely. It like crunched, and it looked very different. They did some Raman scattering, and they saw that the nodes had moved, the actual not reflections, the spectra had moved, and they were like, this has made a new material. They were like, this is bonkers. They didn't really know what else to do with that, but luckily for me, I was giving a talk in America and about some work I'd done on Europa minerals, where I found some new minerals and I solved some structures. And so in the coffee break, this guy came up to me and said, oh, hi, I'm Rob, I'm from JPL. We think we found a new material. We don't know what to do. Can you help us? And I was a bit like, okay, fine. And this was 10 years ago, and now we've had very good collaboration, and we found about 8 different new materials now between us, and we literally just scratched the surface. So the very first experiment, Rob came out to Australia, and we sat there and we found this new material, found it with diffraction. We solved the crystal structure, and we both looked at us and each other and were like, well, that's our research career sorted now. That's like 20 years of stuff we've got to do. And we're condemning some students to looking into it as well, and things like this. And we're at the moment. So what happens is this structure is that the benzene actually forms a beautiful framework. So the benzene makes like makes little channels, and the ethane lives down the channels as well. It's a really beautiful little structure, benzene ethane co-crystal as we call it. And then we've since found that other small molecules, so acetonitrile, so another group found this, which was really cool, that another molecule can live down that same channel. The structure is almost the same, it's a small modification, but it allows. And so now it's like, ooh, what else can live down there? Like, can hydrogen cyanide live down there? Like, we're looking at all the molecules that we found. And this is only binaries. This is only 2 materials. We haven't even started thinking, what if we mix 3 things together? So it's we're pretty busy, which is amazing. It's really fun. So
I love the whole mad scientist aspect of it. Now we're going to mix this. We're going to mix that. It makes me feel like I had my chemistry set when I was a kid. Just what the hell?
I mean, yes. I mean, I'd like to think we're a little bit, but no, that is exactly us. What if we do this?
Oh, God.
I have to ask, somewhat off topic. And we're kind of getting close to the time, but I have to ask. This is my favorite thing. Well, no, one of my favorite things for getting ready for today. Who is Dr. Bunhead, and how did you make the world's longest glow-in-the-dark necklace?
Yeah, that was another weird temp job that I had. So essentially, after I finished at the RI, I was sort of Andy and I, my other half and I, we travelled a bit. While I was travelling, I'd had the interview in Australia, and we'd got back to the UK, and we were just sort of like, I'd been offered the job in Australia, and I was sort of like just sort of messing around in Edinburgh, not really packing up and everything. Now, Edinburgh has a big science festival in Easter time, and I think because of the RI and stuff, I was basically looking for just little bits of temp work and around the festival. And so I contacted the festival directors, and they're like, oh yeah, Tom needs some help. I'm like, okay, all right, Tom. So Tom, Dr. Bunhead, was a sort of minor science celebrity. He appeared on various shows. There was a show called Brainiac in the UK, and he was like the weird mad scientist on it. He's an incredibly gifted science communicator, and he had got funding from a chemical company, and he was like, right. So he was doing this big show in the Usher Hall, which is like the Royal Albert Hall of Edinburgh. It's like a massive, massive hall, and a big show, fire cannons. Wow, it's like basically everything we did at the RI, but on steroids without less risk assessment, because he's a freelancer, can do what he wants. Not that he's ever blown anyone up, I think, aside from himself. So essentially it was like, oh, Tom needs some help, do you mind working with him? And I like sat down with him, and he was like, right, Helen, we've got to break this world record. That's your job. I'm like, okay. And he's like, well, I've got the guy from Guinness coming. We've got to do this. And essentially, I spent like 2 weeks in his flat in Edinburgh working out ways that I could pump round this chemiluminescent material so that it would still be glowing, because there was like, the whole thing was like 283 meters and 44 centimeters. Then have it looped enough, because the idea was all the kids would come on stage and wear it at the same time. And the really risky thing was the fact that it was all like little loops. So you put little loops, and then there was a space, and then another loop and a space, and you put them all on these children. And all we needed was one 6-year-old to make a runner for it, and it would strangle 3 others. So it was sort of like an exercise of like, I was mainly a sheepdog trying to make sure that nobody was like moving. And then of course we had to also have the material, because it only glows for a certain amount of time. It's a reaction, right? It doesn't go on forever. And so we had to make sure like it was pumped round at the right time. It was crazy. And then because they wanted to, on Tom, like Tom was like, oh, we should turn off all the lights. I'm like, oh great, because this is where everyone's going to run. I'm like, no. But they did. Yeah. And then literally, we then had to measure it. And of course, we'd had about 150 children wearing it. The whole thing got massively knotted up and all sorts of things. But luckily, my hobby is that I'm a knitter. And so my other skills that came into this is I'm really good at untangling yarn. And so I was able to use those skills to untangle this thing. And then the guy from Guinness, Craig, he literally came. Do you remember those little things you had like in the school playground, like they were a measuring device, but they were like a rotation.
Wheel.
Yeah.
You just walk the wheel around. Yeah.
Yeah. He literally had like official one with like Guinness on it. So he obviously measures stuff a lot. And he trundled up and down. We had it laid around the usher hall, and he measured it. And it was another very interesting temp job that I had.
Wonderful.
So become an experimentalist, kids. You never know what you're going to do.
Yeah. Okay. Are we at that point, Kovi?
I'm sorry, I feel like I've just gone on and on.
No, I loved every
phenomenal.
second of it. And I still think that we're going to need at least one additional episode, like a part 2, maybe a part 3. There's so much, oh my gosh, like a wealth of knowledge and stories and knowledgeable stories. But the episode does have to end.
Yeah.
And the episodes always end with our rapid fire round of questions and quibbles. So we're going to do 11, that's prime number, 11 immediate responses. First thing that comes to your mind. Are you ready?
No, but let's go.
All right. Benjamin, you want to start us off?
Sure. What is the weirdest thing you believed as a kid?
That I could be a scientist.
Amazing.
Love that. Love it.
Which teacher had the biggest positive impact on you?
Mrs. Gibson in year 3.
Shut up.
Because she allowed me to do a paper mache Jupiter, and then she hung it up in the wrong place, and I was annoyed.
Even as a kid, that's not where it goes. What is one scientific discovery you wish you could have witnessed in person?
Max von Laury's first diffraction.
Yeah?
If you had to pick one historical scientist to go bowling with, who would it be?
Only one. Catherine Lonsdale, for sure.
Okay. Now it's going to get seriouser. If
Even more
you were a
serious.
sandwich, what kind of sandwich would you be?
Parma, ham, and mozzarella with basil.
Ooh,
Nice.
nice.
Maybe some sun-dried tomato.
What
Okay.
would you say is your most controversial opinion about pizza?
That Hawaiian pizza should not exist.
You know, that's a running thing as we are going
Sorry.
through our guests asking these questions, and I don't understand the hatred towards it. I get that you don't
There are two
want it,
types of
but
scientists. Right? It's a clear split between hatred and love for pineapple on pizza.
well, scientists are very, positive, negative type people. So they're either going to hate it with their full intensity or they're going to love it with their full intensity, and there is no in between.
No, that's true.
What is your favorite scientific word or phrase?
Humongous. I don't think that's a scientific phrase, but I use it a lot.
Good word, though.
If you use it, you're a scientist. It counts.
There you go. What is your least favorite scientific word or phrase?
Utilize with a Z.
Useless.
Okay, that's specific. What is your favorite useless science fact?
That if Jupiter's magnetic field was if you were able to see Jupiter's magnetic field, it would be the biggest thing in the sky.
Really? That's
Actually,
awesome.
not that it's not that. It's actually quite useful for me when I'm talking about radiation on Europa, but but yeah.
If you could rename one planet in our solar system, what would you call it? King of the Dwarfs.
Yeah, I would probably rename Uranus because I really do feel that it has held back research into Uranus because people are a bit scared to say its name. So, and I know that originally it was meant to be called George, and I wouldn't call it George. Yeah, I'm not sure, but I wouldn't call it Uranus.
Poor you.
Poor Uranus. It has a bum deal.
I saw what you. We saw what you did. Last question. If you had to sing one karaoke song to save humanity from an alien invasion, what would it be?
I mean, I'm an Essex girl at heart, so it would be I Will Survive, which is very appropriate.
It would work. That way is appropriate.
Yeah.
On every level.
It is known as the Essex anthem, and I'm not very good at it, but I'd try. For humanity's sake.
For humanity's sake, yeah. Nice. That brings us to the end of questions and quibbles and to the end of this episode. Helen, thank you so much for joining us. My cheeks are hurting from laughing.
It's been lots of fun. I probably have shown myself off to be a bit more of a madder scientist than I intended, but hey.
Oh, that's fantastic. And I pinky swear I'm not going to try and sneak a mouse to the top of the Burj Khalifa.
Okay, cool.
If folks wanted to find out more about your research or your science communication work, where can people find you?
So I'm Crystallized Cricket on Blue Sky. I'm hoping soon that my website, crystallizedcricket.com, will be up online. I haven't quite almost the content. And I warn anyone now that it's not just science. There is a whole nother sporting dilemma to what I do. So I apologise if you talk to me about science and somehow I start talking about women's cricket. It just happens.
Fair enough. How about you, Kovi? Where are you?
Folks, where am I? I'm in Sydney, but if you want to find me, don't come to Sydney. You can look for me online at Fun Fact Science on all of the socials. Benjamin, what about you? Where can folks find you? Where can folks find our episodes?
Just look me up under the name Science Actually, Facebook and Instagram and all the other wonderful things. And if you would like to hear this podcast, just go to anywhere you get your podcast. And if you'd like to watch our faces make the sounds that you hear, You can see that happen on YouTube and on TikTok. I forgot the name. TikTok. It's all up there.
And you'll hear us and see us next time on the next episode of Science Actually Presents The Nerd and the Scientist.
Thank you so much for joining us.
Thank you.
Thank you.